Welcome back for another at-home lab submission. This time we will be exploring operational amplifiers and interfacing them with an Arduino. First, we're going to take a look at this non-inverting amplifier on paper and analyze it using these three rules. The current into the inputs is 0, the voltage across the inputs is equal, and the output voltage is anything necessary to satisfy Rule 1. By applying these rules, we can see that there's a relationship between the output and the input, where the output equals the input times a ratio of the resistors used in the circuit. For exercise 2, I built a unity gain amplifier, also known as a voltage follower. I can use this potentiometer to vary the input voltage to the op-amp between 0 and 5 volts. This green wire directly connects the V- to V out. And since V- equals V+, the input voltage should be equal to the output voltage. I've created an oscilloscope-like view using Arduino to read the voltages and processing to display it on my screen. As you can see, Vin, V-, and V out are all equal and overlapping data points. But as I bring Vin down, V- and V out follow along, except when I get to around 1.9, where Vin continues to drop, and V- and V out stay at that level. This is due to powering the op-amp with 5 volts and 0 volts instead of the 5 volts and minus 5 volts minimum that this op-amp requires. For exercise 3, I built an inverting amplifier as shown here. Since I'm using a single-sided voltage supply of 0 and 5 volts from the Arduino, I'm going to use a virtual ground made from a voltage divider to set the voltage on the non-inverting pin to 2.5, which is halfway between the supply voltage and ground. According to the ideal analysis of the circuit and a gain of 10, the op-amp will be governed by this equation here, which will result with an output of 27.5 and negative 22.5 while varying the input from 0 and 5 volts. Since the voltage supply is 0 and 5 volts, we would expect that these outputs to be clipped at those inputs as the op-amp is saturated. Looking at the circuit, again, I can vary the input between 0 and 5 volts using the potentiometer. And again, I can examine the behavior in processing. The input here is shown in white, and the output is shown in blue. As I increase the input from 0 volts to 5 volts, you can see that the output is clipped and plateaued at between 4.3 and 1.8 volts. The reason why it's not clipped at 0 and 5 volts like I was expecting is because, according to the datasheet, there is a maximum peak output voltage swing, which is between 12 and 14 for a 15 volt supply, so within 1 to 3 volts. You can see that while it is plateaued and the op-amp is saturated, V+ and V- shown in green and yellow are not equal. This is breaking Rule 2. This is because during normal operation, when V out is not plateaued, V out can change to whatever is necessary to keep V in equal to V+ through this voltage divider here. However, once the op-amp saturates and V out is held constant, V- will continue to change with V in. For exercise 4, I built an integrating amplifier. Again, I've used a virtual ground on the non-inverting pin and have derived the expression for the output voltage as a function of the input voltage. As I adjust the input voltage, you can see the behavior of the output voltage as I go above and below 2.5 volts.